What's so funny?
Nothing.
Nothing's funny? Is my, I gotta check if it's bouncing now. La 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 la. Yeah, it's la-laing. All right, let us begin with a word of prayer. Sorry I'm late. There's exciting things going on in the department right now, as usual. Dear Heavenly Father, we thank you for this day. I thank you for the students. Just ask that you'd help us use this time wisely just to prepare for the test, which is soon coming, Lord, and just help these students to all do their best, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So this is the solution to mission 7. Are there any particular ones you guys would like to focus in on at the moment? So here's 64, which none of you care about. 65. No, there are no questions about 65. Not really. Let's see here. So you guys are good on 60, 66? It's fine? Feel good about that one? All right. Let's see here. Here's 68. A couple different things going on here. First of all, I have looked at it a couple different ways. One way to look at it is just to factor out the z plus or minus 2i and look at the whatever's, like the cofactor, if you will, the whatever multiplies next to it, and notice that that's, it's holomorphic and hence analytic, and it evaluates to be non-zero at the points respectively, which shows you that, in fact, plus or minus 2i are simple zeros. So that's like one way to do that calculation, which isn't too bad, right? Because the other way of doing it, to explicitly produce the Taylor expansion around plus or minus 2i would be a lot more work, right? Because if you think about that, you'd have to figure out how to write h1 or h2 expanded about either 2i or minus 2i. That's a considerable calculation, actually. That would take me a page or two, which is the issue for 71, give or take. Any questions about this one? We're all okay on that one. So this one, on the other hand, I chose to actually look at the power series and factor out the z squared because it wasn't too much of a deal, too much of a problem, actually, to look at the power series explicitly and then factor out the leading z squared, and then be left with this analytic function, which is clearly minus 1/2 at 0. And also kind of gives you a window into where part C came from in some sense, right? Because part C is basically given by dividing off that z squared, which makes the 0 removable. But otherwise, I decided not to. Now, again, I haven't actually expanded cosine z about these other points. I guess you could do that. It wouldn't be too bad here, actually. But instead of doing that, I just showed that, in fact, at any even multiple of 2 pi, any integer multiple of 2 pi, rather, we have the first derivative is 0, but the second derivative is non-zero. Consequently, 2 pi n is a double zero. And I mean, here's the explicit evidence in terms of factoring the series for 0, but in fact, this calculation is unnecessary when you add this down here, right? This calculation down here actually shows you that 2 pi n is a double zero for all n. So these are not, this is a special calculation. This is the general solution. What I'm doing here is showcasing a method of calculation for you guys, all right? So don't try to read more into it than that. This one here, if you want to do it by direct calculation, differentiating gives me this for z not equal to 0, right? And if you plug in 2 pi n, you get 0. But if you differentiate again, you get this. And if you plug in 2 pi n, you get minus 1 over 4 pi squared n squared, which is not equal to 0, which shows you directly that for n not equal to 0, it's a double zero. So, of course, I would point out that you could have seen that immediately from the previous part of the problem, because the previous part of the problem already had given us that cosine of z minus 1 is equal to z minus 2 pi n squared times hn of z, where hn is the cofactor corresponding to the 0 n, well, 0, 2 pi n. So we already knew that there's an expansion like this at any 2 pi n because we proved it was a double zero in the previous part. So you could use that to see that, in fact, z minus 2 pi n hn over z squared, well, this is analytic, holomorphic, in fact, for z not equal to 0, and it's also non-zero because of what we already proved in the previous part. So you could have solved this part with just this little paragraph if you wanted to. Yeah. But I don't, whichever way you did it, it's fine. Let me get on to this is pretty straightforward. I'll let you look at this. Here I did problem 67 again. Exciting, right? Problem 70. Supposed to find all possible Laurent series expansions about z equals to 0. So, in fact, we have this global formula, right, for this meromorphic function on the plane, well, extended complex plane even. It's really the sum of 1 over z minus 1 minus 1 over z. So you can see z equals 1 and z equals 0 are singularities for this function. Of course, that was already apparent back here, right? So any kind of Laurent expansion has to kind of respect these singularities in some sense. So let's see here, what am I doing? Around 0, I expect I'm going to get one expansion between 0 and 1 if I expand about 0. And then I'll get a different expansion around 0 if I'm past 1. The details of those expansions are in the next page. The question is what's small, because it's going to be based on a geometric series trick. So like the geometric series trick that'll work in here is modulus of z less than 1. That means I can make modulus of z my ratio. I can make z my ratio for the geometric series. Out here, modulus z is greater than 1. That means I probably want to use geometric series with like 1 over z as my ratio. That's the distinction. Both centered at 0, though. So for 0 less than z less than 1, first of all, that's already a term in the Laurent series, right? 1 over z. It's part of the principal part of the Laurent series expansion about 0. And then this I convert by a geometric series result into that, and there you go. This is the Laurent expansion inside the unit disk, well, the punctured unit disk, right? There's that. Then next, for z greater than 1, still minus 1 over z, nothing to do there because we're centered at 0, so that's already a Laurent series term, right? No manipulation needed for the 1 over z term. But this one, you got to use your imagination, factor out a 1 over z. That leaves you 1 over 1 minus 1 over z. And now we're in business because 1 over z is something with modulus less than 1 in this domain. I say domain, is that correct? Is it a domain? I guess this is a domain. Is it a domain? Yeah, it's a domain, okay. I got to be careful. The domain has a technical meaning in this course, right? Other places you say domain, it could be who knows what it means, right? In another course, domain is just some kind of fuzzy word for a set, usually. And here it's an open connected set, yeah. We would use region for closed connecteds. Well, it's more complicated.
Actually, on the Wikipedia page, it's like region means this, except according to this guy named Kreisig, who says region is what it is.
Oh, really? Yeah. So it's all Kreisig's fault? All right, crazy. I guess crazy me then. So it's good company to have. That guy wrote some pretty interesting books. But anyway, minus 1 over z, and so I do the geometric series again, and bam, there you go. This is the Laurent series expansion for the outer annulus. So for a given center, we get different Laurent series expansions depending on which annuli we're looking at, right? Even for one center, there can be different Laurent series expansions depending on which annulus you're looking at. Now, technically speaking, if you just fix your attention on the Laurent series expansion, I think that will extend to the whole complex plane modulo the, I'm trying to think what, something gets left out. Maybe the center. I don't know, these formulas can have meaning outside of outside of the annulus where they converge to the given function, is my point. Maybe not if you look at the whole thing. If you look at part of the Laurent series expansion, it'll converge out past the inside, and the other part will converge to the inside, right? So they have meaning past the annulus where they model the function, right? But they're most interesting, of course, on the annulus where they reproduce the function. Okay, now, what else is there here? We're also supposed to do what? Expand about, I think, -1, was it? I forget my wording. Hopefully I was true to my wording. What problem were we on? 70. Find all possible Laurent expansions centered about z equal to 0. I think we already did that. There are 2. Find the Laurent expansion about z equals -1, which converges at a half. So there is more than one Laurent expansions about -1, right? Yeah, exactly. The 3 that are possible is the one that goes between, like this little disk here, right, or punctured disk, then this annulus, region 2, and then the outer annulus, region 3. Those are the 3 different annuli you could find a Laurent expansion centered about -1 as it happens. The reason that there are just 2 centered about 0 is it just so happens that 2 of the singularities lie in the same circle. And that's why there's a distinction between these cases, right? Because these, well, is that right?
Isn't it more so that you're centering around the singularity?
Yeah, I'm sorry, I'm an idiot. There's no specific intrinsic meaning to 1 and -1. I said that, but it's just wrong. Sorry about that. It's which I was going to say it's one of you guys rubbing off on me. Which one should I pick? Who should I pick on? I pick on Sam. Is Sam rubbing off on me? But usually you say things that are true, Sam. So I don't think that's quite accurate. Usually. So anyway, long story short, 1/2 is in this region too. So we want to find a Laurent expansion around -1 for modulus 1 less than z plus 1 less than 2, right? So in this is the estimate we have to work with, and so that means that the radius is not z plus 1, is it? That's not going to do it. We could do, I guess we could do z plus 1 over 2. That would be less than 1, right? So we could expand in, if we had like a z plus 1 over 2 appear, or also if we had a 1 over z plus 1, that would be, we'd have control of that. Either one of those cases. So here's what ended up. So when you're working this kind of problem, you kind of have to use your imagination. You have to create the thing you're after, which in this case is z plus 1. So I start with a z, which means I can add 1 and subtract 1. Yep.
For the picture that was in the last picture, so if you chose 1 or 3, then would that mean that it would be one of the times where like the inner circle is 0 or the outer circle is like infinity?
What do you mean choose 1 or 3?
Like if you expanded instead of choosing 2, like the way you have the numbers.
So you mean, suppose I expanded about 1 instead of -1?
Or no, if you use the first expansion, like
Oh,
inside
sorry,
first.
yeah. Like the Roman numeral 1.
Oh, Roman numeral 1. Then I would need to use this inequality to guide my geometric series.
So the like inner circle would just be the point -1.
Yes, right. Yeah, it's a deleted disk, which is, in our thinking, a kind of degenerate annuli. Yeah. So an annulus includes disks, deleted disks, exterior disks. Get all your disks and more. Lots of flavor choices. All right, so after I add 1 and subtract 1, then the next move is to create a 1, right? Because we're always looking for something of the pattern 1 minus r, so we can do the geometric series for these kind of examples at least. And so I do that, geometric series, bam. And so that takes care of this guy. Now this one, see, before we didn't have to do anything to that because it was already a Laurent series term expanded about 0. But this time, it's not. So we have to actually convert it to 1. And so this is equal to 1 over 1 minus z plus 1, which then I can geometric series on that. No, I can't yet, though, right? Why can't I do geometric series already? Because z plus 1 is not an allowed ratio, right? In region 2, z plus 1 is less than 2. That's not going to work for us because this is, if I just apply geometric series on this directly, I'd be wrong because it doesn't converge with that radius. So what I got to do is factor out that z plus 1, and when I do that, I get 1 over 1 minus 1 over z plus 1, which I'm allowed to. This is good news because that has modulus less than 1, which means I can apply the geometric series result. So you got to ask yourself, where are you? What do you have to work with? And then geometric series will usually do most of the work. So in summary, the 1 over z minus 1 over z gave me this Laurent expansion about minus 1. And so I got this piece, which looks like a Taylor piece to me, right? It's positive or non-negative terms. And then this piece over here looks like it's all negative reciprocal terms, right? So this is the singular piece. This is the holomorphic piece, I suppose. Well, this would be the, I guess I couldn't say that it, let's see here, what should I say? What's that?
The left is F0.
Oh, this is F0 and that's F1? Yeah. Right, I was about to try to classify the singularity. I was about to say, oh wow, minus 1 is an essential singularity. Why is this nonsense? Why is, I mean, look, there's infinitely many reciprocal terms, right? There they are. What happened to that? Oh, here they are. Infinitely many reciprocal terms that came from here. So doesn't that make minus 1 a essential singularity? If you have infinitely many reciprocal terms in the Laurent expansion, isn't that an essential singularity? Only if you're on a punctured disk. How about only if it's first a singularity? Right.
Well, you define a singularity as looking at the punctured disk.
Right. The point, yeah, but I guess what I'm trying to say is we can always puncture a disk, and then say from the Laurent series expansion of this given function about the punctured disk, even whether or not the inside puncture actually has anything to do with a genuine singularity for the function or not.
Right, but then if it's not a singularity, if you're doing it in the punctured disk, this will still work.
Is minus 1 a singularity for this? Oh, but minus 1 is also not in this region, is it? Right. Okay. So yeah, I'm processing what Sam was saying. I'll get with him eventually. The point is that minus 1 is not even a singular point here. So we can't analyze whether or not this tells me, like, is it an essential singularity or a polar? It's not even an appropriate thing to be thinking about. Right. The deeper thing Sam was talking about is if we're going to analyze the type, the class, if we're going to classify a singularity, we need to be looking at the Laurent expansion on the punctured disk near the singularity. You don't look at the Laurent expansion on an annulus, which is around the singularity, but not. It's got to be the punctured disk near the singularity. That classifies the type of singularity, right? That's the fine print that we could get confused about if we're not careful. Yeah. Now, this This one here, guys, that I had questions that took me until, like, I was answering a student's question until about like 11:05. I was planning to fix this solution in, oh, wait a minute. No, this one's fine. I'm getting ahead of myself. Any questions about 71? Let's see here. So what I did was use the adding angles formula to, like to convert to either a minus sign or a plus sign of z plus pi over 2, yeah, from cosine z. And after doing that, it's easy enough to write down the power series expansion centered about pi over 2 or minus pi over 2. And then you can see that one of these guys will cancel with that. And that just leaves you a removable singularity. Same for both of them, because the offending term in the denominator clears out with what's in the numerator after you make the appropriate expansion, which says it's removable. Let's see here. What did I say? It's debatable, but you might also consider infinity. I said grader, do not penalize you guys for that. By the way, the grader says that he has not graded your homework yet, but he will try to grade it, and so I might have something more to get back to you tomorrow. We'll see. If it happens, I'll email you. Okay? Or if you see the grader, you can go up to him and say, "Hey, grade my homework, please. I'll get you some chips. Barbecue Lays is what you'd bring to him. Preferably in 3. Get him 3 bags. He likes 3 bags. I've watched. No, little bags. I've studied his method. If he has 1 bag, he has 3. He will always eat them in groups of 3. I've studied this. It's a theorem I have. It would have a very limited readership, but I would like to write that paper. Why not? I've harassed him about this already. He knows. Anyway, so if we were to study infinity, then let's see here. At infinity, I can pull a 1 over z squared from that term, right? But the cosine z, oh man, that's bad news, right? So essentially, cosine z's got an essential singularity at infinity. And this is analytic at infinity, this piece right here, right? But there's no way that this times that somehow cancels out to give you finitely many positive power z terms at infinity, which is to say that this clearly has an essential singularity at infinity. I am completely open to you giving me these kinds of intuitive, not quite rigorous arguments if I say, analyze the function to decide whether or not it has an essential singularity at infinity, right? Something like that. I mean, if you wanted to be fussy, it might be a lot longer argument. This one, I don't know, there's various ways to do it. I decided to look at the partial fractions decomposition of that. And so when I found it was this and that, which allows me by laws of exponents to give me this and that. And each one of these is analytic at the other one. So like this is analytic at z equals to I. That is analytic at z equals to minus I. And so and there's no way for, I think, this to cancel with that if you multiply them out. So in short, I see that they're both essential singularities. Now, this argument, maybe there's some holes, right? You could fuss. What would be a better argument here would be for me to use the Casarati-Weierstrass and to just produce for you 2 different sequences which approach plus or minus I, let's say. Let's just say I for the sake of discussion. I could find 2 sequences which approach I, and yet the limit as we approach I gives different values along the different paths. That would be a better way to do this problem. All right? I was a little bit of a hurry when I was writing this. I forgot that's what I wanted to do. That's really what I should do to give you a better argument. And if that's what I wanted you to do, I might even say so in the test question if I were to ask it, right? I might say, use the theorem of Casarati and Weierstrass to prove that this is an essential singularity.
That wouldn't actually be using that theorem, right? You more are we using the theorems of, like Riemann's theorem and then the theorem on poles approaching infinity? Because you're saying like it doesn't satisfy those, therefore it must be essential. Because already Weierstrass is the other way around.
Yeah, Weierstrass says that I can find a limit for any number in the complexes.
There's some sort of logical operation we can do through the Weierstrass theorem, which, like the negation of it, perhaps, or.
I don't think so.
I don't think it's a big.
I mean, the proof of the Weierstrass theorem is what you guys are saying. So, I don't know. Can you guys think of what sequences you would look at here? Maybe, how about z approaches I? It shouldn't be hard. If you just pick like a real sequence versus an imaginary sequence approaching I, it should work out somehow different.
You approach it from below and above, and you get
Just above and below works out fine? Okay, cool.
What I did is what I said, like, if you approach either of them from starting at 0, you
Mhm.
get one thing, and if you approach either of them starting at infinity, you get it. Or specifically, like, starting, like,
I think that's a better way to do this problem, because this was kind of like laborious, this calculation I did. Now, part C, I've got an error in here somewhere. I don't know where yet. I got to fix it, guys. I'm sorry. Because, look, whatever happens at 1 should be whatever happens at -1, right? There's a symmetry to this problem. They're either both double poles or they're both single poles. There's quite clearly a symmetry between 1 and -1 with this formula. And yet, when I did it 2 different ways, I got 2 different answers. So there's something wrong with my calculation, obviously. So first of all, I was able to prove that both were double poles. This, I believe, is correct. But then I was like, well, I want to calculate the principal part, right? So that means I need to expand about the singularity. And so I tried to do that. And so here it is, expanding around z equals to 1. Where was I? So I'm expanding this H2, right? Yeah. So basically I'm focused on expanding the H2, which if you look at it, if you add 1 and subtract 1, that gives you a z plus 1 over z plus 1, which is 1 over z plus 1, and then minus 1 over z plus 1 squared. And then, well, this one, now that's lovely, but still useless because we need to expand about 1, right? So I do the usual song and dance. I subtract 1 and add 1. That gives me 2 over z 1 over 2 plus z minus 1. And then this one here. Let's see. And then, so that one's, after I factor the 2 out, I can do geometric on that. But I decided at that point to stop because it was getting kind of like I didn't have room on that page. So I thought, yeah, I'll just use geometric. I'll use Taylor's theorem instead. And so I decided to do Taylor's theorem on this piece. And when I did that, I had like g prime, and here's g prime prime. So if you like plug in 1, plug in, 1 into the function, the derivative, the second derivative, I can see from the outset that this is holomorphic at 1, consequently analytic at 1, which means I can produce the Taylor series by using Taylor's theorem. And if you think about finding the principal part, it suffices to find it out to linear order, because that's where the principal part's going to come from when you multiply by 1 over z minus 1 squared. So I really don't have much to work to do. I just need to find the first couple terms in the Taylor expansion here, and I should be good to go. So I tried. And when I do that, I end up getting, g of 1 is, well, looks like to me 1/2, no, 1/4, 1 over 2 squared, 1/4, and then g prime, what's g prime of 1? I think I get a quarter minus 2/8, otherwise known as 0, and then g prime prime of 1, I ended up getting, I guess, minus 1/16, because I got minus 2/16, which is minus 1/8 rather, then the 2 from the Taylor's expansion multiplies that to give me minus 1/16. So I ended up getting that the principal part was just 1 over 4 times z minus 1 squared. I'm not sure I trust that result. Because when I did the other one, which I decided to do by full geometric tinkering rather than Taylor expansion, so I decided to try to chase the calculation I was starting on the previous one for the other pole. So again, subtracting and adding 1 gives me 1 over z minus 1, and then plus 1 over z minus 1 squared. This is not geometric to start with, but I can make it geometric by integrating and shifting and then differentiating to get back. So if I did that right, this is the expansion for g of z, just this piece of it, about minus 1. Wait a minute. Yeah, about minus 1. And likewise, the geometric series trick there gives me that. So 1 over z minus 1, I get that expansion. I got the star, I got Pac-Man. And then when I put down the first couple terms in star and Pac-Man, Pac-Man gives me n equals 0. I got minus 1 over 2, so minus a half. N equals 1 gives me minus 1 over 4, so minus 1/4 z plus 1. And then n equals to, what's it, 0, 1, 2. N equals to 2, 2 to the 3, which is 8, minus 1/8 z plus 1 squared. That's what my Pac-Man. My star, when I expand this guy out, I got 1 over 4, z plus 1 to the 0. Then n equals to 2 gives me 2 over 8. Wait a minute. 2 over what? Wait, what? Wait, what? N equals to 2. Hey. Ah. That should be an 8. Right? Because n equals to 1 gives me 1 over 2. No, 1 over 4, right? Let's try that again. Star. N equals to 1. 1 over... That should be a 4th, right?
Yeah.
So that's supposed to be a 4th. That's supposed to be a what? 2 over... That's supposed to be 2/8. Because n equals to 2 gives me 2 over 8. That's 2/8. And then I should have 3/16. And so I don't get these canceled directly. In fact, I got minus 1/2 plus 1/4, which would give me minus 1/4, actually. And these don't cancel. These actually give me... Well, anyway, what I'm trying to tell you is I guess that maybe it's just this part of the calculation that's flawed. I'm not sure. I just know there's an error in here. Yeah.
And then if it would be just 1/4, there would be a z plus 1. So then you end up with minus 1 over 4 times z plus 1 squared.
Is there anything else in the print? Is there like a reciprocal term as well? Or does the 1 over...
No, maybe like the first thing in those brackets would just be 1 or minus 1/4 maybe.
What's the next thing? Is it like order...
Something times z plus 1.
So there is a z plus 1 term?
I only got.
Oh, no, sorry. I don't think there is.
So what's this actually supposed to be? That's...
Just end up with
Yeah, there should be a z plus 1 term.
So that this piece, what is this? When I put n equals to 2, I get 2 over what? 2 over 8, which is 1/4. So this does cancel with that if I do the math right. And we're just left with a minus 1/4 here. And that is a lot like the so, okay, I feel better. Because then that matches what I found in the previous case up to a sign. And I'm willing with there to be a plus minus difference between the different singularities. But the principal part should look an awful lot alike. There's a symmetry between 1 and minus 1 for this formula. So, yeah.
What I did is I just found algebraically the partial fractions decomposition.
Uh-huh.
So it's pretty straightforward, and then you end up with those two terms.
Nah.
And then according to theorem 11.4.2, that gives the principal parts right.
Ah, very good. So I like Sam's way better. So Sam's like, instead of doing what I did, just find the partial fractions decomposition of the function, which is a perfectly reasonable approach. I love the Laurent series result, and I love it too much sometimes, you know? So Sam is saying, instead of doing what I did, you just look at this and go, aha. So this can be rewritten as a over z minus 1 plus b over z minus 1 squared plus c over z plus 1 plus d over z plus 1 squared. And after about a third a page of algebra, you can work out a, b, c, and d. And then we know from our work on the partial fractions decomposition of rational functions that those are in fact the principal parts of the Laurent expansions about the respective poles. So like,
We just have A and C are 0, B and D are plus or minus.
cool. That is a much better solution. I like it a lot. Yeah. But I hope that my solution here is not useless to you either. The calculational techniques that I'm using in my solution are important for you to know about. But Sam's approach to this problem is by far superior to mine at the moment. Totally agree. Yeah, Jonathan?
So once we figure out that minus 1 and plus 1 are double poles,
Yeah.
that like automatically tells us that your original second principal part has to be wrong, right? Because it has to be order 2.
Oh, no. The double pole means that the most negative power appearing is 2. But it could be, you could have a pole of order 2 and have, like, for example, z equals 0. You could have 1 over z squared plus 3 over z plus 1 plus z cubed plus z to the 17th plus da. That would still be a pole of order 2, even though you had a 1 over z squared and a 1 over z term.
Right.
So,
But you know that you have to have at least a 1 over z squared term, and then maybe something in between.
yes. Yeah. If I didn't have the 1 over z squared term, and it's no bueno. It's not cool. All right, well, I think I have focused entirely too much on this homework for you guys. There, of course, is stuff we did before, right? What were those things? Do you remember? It was a simpler time. A time before singularities. Oh, not calculus 1. Let's not get that simple. I mean, I can put epsilon delta proofs on the test if you'd like. You're fine with that, you monster. Where were we? So an ML theorem is a good problem. I hope that you have taken time to learn the basic inequalities we have to work with, right? Really look at it. We have the triangle inequality, and that I sometimes call it the reverse triangle inequality, the one that allows us to, how's it go? If we want, man, how's it go? Z, I can't even remember. I want this to be greater than or equal to something. What do I do? Is there something I can put there? Absolute of z, I think it's minus absolute of w, isn't it? Is this correct? Well, I'm going to erase it then. There seems to be some squinting. But
Was it minus in the first one?
there's a minus in the first one as well?
No, it was on something else.
Maybe I'll write that on this. Is this correct?
You guys got to, settle that stuff for yourself. Said somewhere in the notes. Okay.
Because you use like the square root of 6
It's,
in R. The square root of 6 in R, right? Yeah.
so where it probably first came up is so long ago that, oh man, son of a gun. Huh. Curses. Ow.
Maybe the place that you use it, you don't call it triangle inequality.
Yeah, I don't think.
Well, it's not, it is not the triangle inequality either. I mean, what I'm talking about is not the triangle inequality. It's a corollary to the triangle inequality.
It's logically equivalent to triangle.
It's logically equivalent to the. Don't get me started.
All the math is logically equivalent to each other.
That's what I said.
Yeah. I can't be around you guys. Let's see here. Ah! Curses. Let me go back to a simpler time. Oh, an even simpler time.
I think that makes sense. Just wasn't thinking you
There we go.
gotta think of it like
This is usually the sort of thing I say early on with, the discussion of modulus and stuff, but that got lost in the shuffle here because we were doing acalculus stuff, yeah. But anyway, here it is. Yeah, modulus of z minus w is greater than or equal to the difference of the moduli. Yeah. So that is sometimes useful. All right. And since that this is either positive or negative, right? So you can wrap that in inequalities without damaging it. I mean, you can put absolute value here without changing anything, right? Because either it's just equal to its own absolute value, or its negative absolute value is still less than that. So either way you go, you can put absolute value bars around that. Okay. So now, I guess in summary, I tried to give you guys a good list of problems I'd like you to be able to do. Beyond that, you need to know what the definition of the complex integral is, how to do calculations from the definition, right? That list of things I gave you to prove, that I think gives you a pretty thorough review of our central calculational technology. Besides just being good things to know how to prove, it actually should help you sort of internalize the discussion we've had in here and the larger theoretical points we've made. In terms of basic integration, we had 3 different definitions I presented, and I showed you how they're logically equivalent. Those things matter, especially as they relate to the ML theorem, right? You got to pick the right starting point, otherwise that's really hard. This problem, first problem in the homework, was a good example of how we can do a calculation with the ML theorem, I might ask something like that. We talked a lot about uniform convergence. You should make sure you know what that is. Weierstrass. There are like a lot of very simple Weierstrass M-test questions that I could ask on the test. We had one of those in the homework that was really simple. So, you guys have an hour test, so I do tend to gravitate towards the problems which don't require a lot of time to think through and yet illustrate a concept. So as I think about a priority list, I would say, as you look through those proofs, make sure you nail down the easier ones first. It is very likely I'll ask you one of the more technical linchpins to the course, like what are those in that list of 30 things I gave you, 29, right? What were the 3 in there that were hardest? Taylor series, Cauchy's integral formula, and probably the Laurent series. I think I said just the the uniqueness. I said just the uniqueness, not the existence, if I recall correctly. Because Sam has still managed to put some lingering question mark about the existence part of my proof. So I'm steering away from it. I think it's right. But
Integral formula, the Cauchy integral formula.
yes.
I'm pretty sure it said n equals 1, but the one we did in class, I think, was 0. Is that, or like, did you want us to know?
Oh, I meant m equals, oh, it depends on how we enumerate it. I meant the one where you have the function is equal to 1 over 2 pi I times the integral of the function of w, dw, over z minus w around the appropriate circle. That's the one I was talking about.
So you could also call that 0, right?
Yeah, depending on what we mean by m. Yeah, fair enough. I meant the simplest. There's two things. The Cauchy integral, which says that the integral of a holomorphic function, is 0. And then the Cauchy integral formula is the next thing past that. But anyway, just do your best. All right, that's all you can do. And I'll try to write a fair test that won't be too crushing. Will there be geometric series on this test?
Yes.
Yes, there will be geometric series. That much is certain. Thanks, guys.